Okay, so the first thing we're going to start with are called ordinary differential equations, also known as ODEs for short. So what are these? Ordinary differential equations are basically equations or an equation involving, and I'll just write out the definition here, involving an unknown single variable function. That's important. That's what makes it an ordinary differential equation, and we'll see the other kind of equation that we could see in the future. So an equation involving an unknown single variable, so single variable function, okay, together, and not only just one function, but together with one or more of its derivatives, Okay, and I'll give some examples below. So derivatives there. Alright, so here's some examples. So i.e., we could have a differential equation, an ordinary differential equation. It looks like this. dy dt is equal to y, which is a function of t, plus t. So in this case, our single variable function, our unknown single variable function, is y of t. We have our independent variable here. This is the variable itself, and then we have its first derivative, the first derivative of this function, this unknown single variable function, right? So this would be the case where we have the function, okay, our unknown function together with one of its derivatives, right? Because this is like y prime. So this one here could also be rewritten as y prime is equal to y plus t. This is also an ordinary differential equation. Okay, here's another example. We'll do a quick one here. We could have something like y double prime plus y prime is equal to y plus t. So in this case, again, here we have our single variable function, which is y of t, that's unknown. We have it together with its first derivative and its second derivative, okay? So this is also an ordinary differential equation here, okay? Okay, so the next topic we're going to go over is called the order of an ODE, of an ordinary differential equation here. So a lot of this video, or a lot of this section, is about just introducing some terminology that we use when we refer to things regarding differential equations, okay? So here we have order of an ODE, and this is basically just going to be equal to the order of the highest derivative of our unknown single variable function, right? So of the highest derivative that occurs in the equation. That occurs in the equation, meaning the ordinary differential equation, right? So for example, the one that we had before, our dy dt is equal to y plus t. In this one, we have our unknown function, right? And that's basically to the zeroth derivative, right? Because we haven't derived it at all. But then here we have the first derivative. So in this case, the order of this equation is equal to 1. So it's to the first order. Whereas the other one that I showed you, the y double prime plus y prime is equal to y plus t. Now here, the first derivative is not the highest derivative that we see, but instead it's the second derivative. So here we would have, this equation has order of 2. Okay? Alright, so something else you might be thinking as well, right now we just learned about ordinary differential equations, but are there other kinds of differential equations? And the answer would be yes. There are what are called partial differential equations, and these involve taking partial derivatives, or not taking partial derivatives, but it just involves partial derivatives of multivariable functions, partial derivatives, I'll just abbreviate here, of multivariable functions, okay? And these ones, even though that sounds super complicated and everything, we will not be dealing with these. We will not be dealing with these in this course, okay? Working with these, okay? Working with these. So you don't have to worry about those at all, okay? Alright, so now we'll go over normal form. And what is normal form? This is basically when our equation has the highest derivative that occurs in the equation, the highest derivative when it has it isolated on one side of the equal sign, basically. So when it has the highest derivative of a function, or of our function that we're looking at, by itself on one side of the equal sign. On one side of the equal sign. Of equals sign. Okay? An example of this would be, just in general, this looks like y to the nth power, or to the nth derivative, right? So this is the nth derivative of a function y, and then on the other side we have some function, we just call it a function of t, of y, and then everything up to where we have y to the n minus 1th derivative, or n minus 1st derivative. Anyway, so basically an example of this would be, okay, so we have y prime minus t is equal to y. So then we look for our highest derivative that occurs in the equation here, and the highest derivative is the first derivative of y, right? And then we have to see, okay, we have to decide, is it by itself on that side of the equal sign? And the answer here is no, because we have this minus t sitting there. So we don't want that. This is not in normal form. Not in normal form. Normal and form. Okay, so how could we transform it into normal form? All we have to do is get this y prime by itself, so we just add the t over to the right side, and we get y prime is equal to y plus t, and then we look, okay, so this is the highest derivative that occurs, and it is by itself on that side of the equal sign, so this one is in normal form. So normal form for this guy, and that is good. We'll be doing some practice problems with getting equations in normal form during the practice problems video, okay? Okay, so now we're going to get into the good stuff. So what is a solution to an ordinary differential equation? So this is basically going to be a differentiable, and I'll just abbreviate to make things go by quicker. So a differentiable function, okay, and usually called like y of t or x of t or whatever variable they're using for your function, that satisfies, and we'll go over what satisfies means in this context of ordinary differential equations. So the ODE, for all, and this is just technicality, so for all t where our function is defined, where y of t, our function, is defined. And again, like I said, we don't have to be using t's for our independent variable. We can use x's here just as well. We don't have to use y here for the name of our single variable function, and you will see it where it's different, like an x of t instead or something like that. Okay, so let's do, I'll just show you an example of what a solution looks like. So here's an example. Let's say we have the ODE of this. So y prime of t is equal to 1. This is an ordinary differential equation because it involves some function y of t along with together with one or more of its derivatives, and in this case we have the first derivative, right? So a solution to this, I'll just give you the solution here because we haven't figured out how to solve for them yet. We will in later sections, but let's say the solution is y of t is equal to t plus 1. And how do we know this is a solution? This thing is a solution, so this is a solution because of the following, and I'll show you why. So if we were to try to plug everything into this thing, it would work out. That's what it means. The word satisfies means, well, when you plug everything in regarding to this function, this solution function, it should work out with the ODE that we were given. So what is y prime of t? Y prime of t, if we look straight from here, that's equal to, when we derive this with respect to t once, we just get is equal to 1. And this is exactly what is on the left side here, so 1 is definitely equal to 1, and that works out. The ODE is satisfied. Therefore, that means that this equation here, which I've boxed like multiple times at this point, y of t is equal to t plus 1, that is a solution of our ODE. Okay? Also, something to note is that let's say we have some other function. Let's say we have some other function x of t, okay? So this x of t is equal to, let's say, I don't know, a t minus 1 or something like that, okay? So let's see when we derive this guy, when we take the first derivative of x of t, so that would give us x prime of t, right? Then when we derive once with respect to t, we still get a 1 out. So that means that this equation, even though it says x prime of t instead of a y there, this just means the first derivative of our function is equal to 1. And that also satisfies our original ODE here, right? So what does that tell us? I mean, in this one, in our y of t, we had t plus 1, and in this one we had t minus 1. And if you think about it, if we had t plus or minus any kind of constant, right, any kind of number, then that would still be a solution because a constant goes away when you derive the first time, right? So I'll show you what this means on the next slide. So this means that we could have what is called a general solution. So let me write that out. General solution. And the definition of this is basically a set of possible solutions. Possible solutions. I'll just abbreviate here. So possible solutions of a certain form. A certain form. And this is also, of course, 2 or 4 and ODE. Okay? So what does this mean? Well, as for our previous problem, our y prime of t is equal to 1. Remember how we had y of t is equal to t plus 1. We had x of t is equal to t minus 1. So a general solution to this ODE here, so this is our ODE, right? So a general solution, so the general solution would be something like, let's say, I'll just say y of t is equal to t plus c, where c is our constant, where c is a constant, okay? And constant just meaning a number form, not a variable, okay? So this is our general solution here, alrighty? And we also do have what's called a particular solution. So that's basically kind of like the opposite of general. General just means like you can vary by constant. Your solutions can vary. This contains the entire solution set kind of thing. But we also have what's called a particular solution. So let me show you what that entails. So a particular solution is basically a unique meaning there's only one of them, unique solution to an initial value problem. Okay, so now we're getting into some other terminology here, and I'll explain what these all mean on the next slides. So to an initial value problem. And these are also referred to as IVPs because, we like to abbreviate things to make them shorter. So anyways, a particular solution basically just allows us to pin down this constant c. So in order, let's say we find c is equal to 2 for our initial value problem, then our particular solution to that initial value problem would be y of t, for example, is equal to t plus 2 if we figured out what our c is. Anyways, we'll continue this on the next slide, okay?